Oh, welcome to a new unit. We're going to be addressing lots of number theory topics in this unit, starting out in this video with basics on prime numbers. But we'll go, have two videos on prime numbers, and then we'll get into some other topics as well. Before we do, I just wanted to go over a little bit about complex numbers. Complex numbers you have seen in algebra classes previously. They are of the form a plus bi. And actually, you've been seeing complex numbers ever since you first learned to read numerals. When you have a number like 3, that's a complex number because it can be written in the form 3 plus 0i, where the 3 is the real part and the 0 is the imaginary part. But since it's plus 0i, that doesn't really have much bearing on it, so we don't try to confuse little preschoolers and putting those 0i's in there. Instead, we just say 3. And we just first, are trying to teach them how to identify the numeral for 3, and then also talk about quantity 3, like 3 fingers, 3 balls, whatever. But you're a lot more advanced than that. Some of you probably have children that are at that age level, and you're probably working on teaching them some of the basic concepts, but you're much more advanced, of course. So I just wanted to go over a little bit about the categories of complex numbers. So if you have a kid and you're teaching them how to count right now, you're down here at the bottom left of this chart doing the natural or counting numbers, which are 1, 2, 3, 4, 5, 6. The ones we naturally learn to count with. We start with 1. We don't naturally think about 0 first. We start putting toys and counting them, or we start putting our Cheerios and counting them, or whatever. Then as a little more advancement comes along, then you end up incorporating 0, and that's the whole numbers. The whole numbers are 0 plus the natural numbers. Then probably about 4th grade, you really start to deal with the negative numbers. You can start dealing with them sooner than that, probably even in 2nd grade if you have money and you start thinking about borrowing money to buy something, and your mom or dad or grandparents or whoever might say, all right, I'll give you the money in advance on your allowance, but you owe me. So as soon as you start thinking about owing people something, you're starting to grasp negative numbers. And that's where we get the integers. That's the whole numbers plus their opposites, the negatives. Then about 4th grade, 2nd grade, I think, is when we first start really introducing what a fraction is. 2nd and 3rd grade. 4th grade, you start doing operations with fractions, like addition, subtraction, usually, unless you're a little more advanced. But so once you start adding in those fractions to the integers, that's all those numbers in between the 0, 1, 2, and the -1, -2, -3, then you have a grasp on the rational numbers. So the rational numbers include everything below them, plus the fractions in between. And these are all part of the real number system. Middle school, start getting algebra and geometry concepts. So you start looking at numbers like pi and e, irrational numbers. These are decimals that go on and on and on forever, never stop, never start repeating over. So pi is a famous example. We have a supercomputer that's taken pi out to over a trillion decimal places, and it can keep going because pi never ends, and pi is not going to suddenly just start over somewhere. E is one that you might see in algebra class, like when you're doing certain financial math equations, like P equals E to the RT and stuff like that. Or you might see it in science class too. Start looking at like decay and growth and things. And then those are part of the complex number system, because all of those numbers can be written in the form a plus bi. Because you can write like -2 plus 3i. You can write -8.5 plus 0i. You can write them as you can put the different numbers into the complex number form. Imaginary, that's when you start having having something other than 0 in there. That's where I wrote the -2 plus 3i. I introduced imaginary there. I represents square root of -1. I squared is -1, so that's real. But then you get to I cubed, and you get -i, And you get I to the fourth, and then you're to plain old 1. So you got I represents square root of negative 1, and then I cubed is I negative I. But you can square I or raise I to the fourth power, and you get back real numbers. But that's where you start dealing with imaginaries. And those are all part of complex numbers too. Like if you have the number 5i, that's a complex number that can be written as 0 plus 5i. So that's the breakdown for complex numbers. For now, for the number theory, we're going to be dealing a lot with the whole numbers and the natural numbers. Might sneak some integers here and there, but you're going to deal with natural numbers a lot with some of the topics we're about to cover. Okay, so moving on. As promised, we're going to talk about prime numbers. Prime numbers are natural numbers. So like I said, we're going to be dealing with natural numbers a lot. Numbers 1, 2, 3, 4, 5, 6, 7. No fractions, no decimals, no negatives, no 0. And it's a number greater than 1 that only has factors of 1 in itself. Examples are like 2, 3, 5, 7, 11, 13, 17, 19, etc. Because like 2 only has factors 1 times 2. 7 only has factors 1 times 7. They're prime. Composite number is a natural number greater than 1 that is not prime. It has other factors besides 1 in itself. Put 4 in as an example. 4 has factors like 1 times 4, but it also has 2 times 2. So that makes it composite. It has something other than 1 in itself. 10 there has 1 times 10, 2 times 5. So that's composite. The 1 is defined as neither prime nor composite. It's its own thing. But anything greater than 1, natural number-wise, is either prime or composite. Now the sieve of Eratosthenes was developed by Eratosthenes of Cyrene, and it's a very systematic way of helping define prime numbers. You can find, like if somebody asked you, what are all the prime numbers from 1 to 100? You can use the sieve of Eratosthenes to find them. We are going to just find the prime numbers from 1 to 30. So you write out 1 to 30 in the chart like I did there, like 1 through 10, 11 through 20, 21 through 30. And you could keep going as high as you want, but we're just stopping at 30 for time's sake. And what we're going to do is we're going to cross out 1 because it's neither prime nor composite. And we're going to say, okay, 2 here. You'll notice I have it underlined, but I'm going to go ahead and circle it. 2 is prime. It only has factors 1 times 2. But as soon as you get to 4, like its multiples, like 4, 6, 8, 10, 12, 14, those are all going to have factors including 2. 4 has 2 times 2, 6 has 2 times 3, 8 has 2 times 4, 10 has 2 times 5, and so on. So these are all composites. All these multiples of 2, have factors that include 2. So that, by the definition of prime, makes them not prime, makes them composite. So 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Those all go over to the composite list. And once you're done with that, you go back to the 2. The very next number that's available is 3. It's not crossed out yet. That number's prime. Each time, the very next available number will be prime. So 3 only has factors 1 times 3, but its multiples will be composites because they'll have factors of at least 3 times something. 3 times 2 is 6. Well, 6 is already crossed out because it's also a multiple of 2. 3 times 3 is 9. We'll cross that out. 3 times 4 is 12. Already crossed out. 3 times 5 is 15. Cross it out. 3 times 6 is 18. Already crossed out. 3 times 7 is 21. We'll cross it out. 3 times 8 is 24. Already crossed out. 3 times 9 is 27. We'll cross it out. 3 times 10 is 30. Already crossed out. Okay, going back. After the 3, the next available is 5. 5, 10, 15, 20, 25, 30. So all the multiples of 5 are crossed out. Back to 5, very next number available is 7. 7 times 2 is 14, 7 times 3 is 21, 7 times 4 is 28. We already had those crossed out. Very next number available is 11. 11 times 2 is 22, already crossed out. 11 times 3 is 33, which is off our chart. So we'll stop there. Very next number available is 13. 13 times 2 is 26, already crossed out. 13 times 3 is off the chart, 39. If you'd had a bigger chart, you'd have to still be doing, crossing out multiples of 13 and stuff. 17 is the next available one. 17 times 2 is 34, which is off the chart. So since you're already off the chart with 17 times 2, all of the remaining available numbers are going to be prime. Because you're not, at this point, you're not going to be crossing out anything else. Because you'd be off the chart. So 19 has to be prime. And of course, 19 times 2 is 38, which is going to be off the chart. So every single remaining number available here is prime. So you now have all of the prime numbers from 1 to 30. 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. So we can thank Eratosthenes for that nice little tool to help us systematically find prime numbers. A little bit more about Eratosthenes. You want to add him to your mathematician list. He was known for being the first to accurately estimate the Earth's diameter, which was a pretty impressive feat back then because they did not have space travel, they did not have satellites, they did not have calculators and computers that we have. They didn't have any of that stuff. He used shadows that he observed on Earth, estimates of distances between places, and then some basic trigonometry. In fact, he was looking at wells. Like he was in one town and city, and he'd look at like high noon, what the shadow looked like that was cast at that well. And then he would walk or travel to another city. He would estimate the distance between the two cities. He'd look at the shadow at noon cast by the sun at that well. And he'd use some basic trigonometry techniques and be able to figure out information between those two cities and then use that to help estimate the entire diameter of the Earth. Pretty neat. Also served as the director of a very famous library in Alexandria, Egypt. It was like the library of the world at the time. So being director there is a very prestigious position, very big, very well known. Unfortunately, he lived a good long life, but when he was 80 years old, he was blind, got really depressed, felt like he couldn't do much more in his life, felt like he needed to be productive and he couldn't be productive anymore, so he voluntarily starved to death. I've heard of people doing that. I cannot begin to imagine. I love my food, so that would not be the way for me to go. But anyways, that's what he did. Okay, another little thing, like after talking about prime numbers, we'll use prime numbers again in the near future. But before we do, I wanted to go over a nice little tool called divisibility rules. Sometimes when you're trying to find prime factors and do other kinds of factorizations, it's helpful to know what numbers divide evenly into the number you're working on. And that's where the divisibility rules come in. They make it a little easier to kind of start guessing and using things. If you're looking at a number and you want to decide if 2 goes into it evenly, just find out if the number's even. And if it is, then 2 does go in evenly. So then you can use 2. If you're wondering about 3, just add up the digits. And if that result is divisible by 3, then the entire number is divisible by 3. Nice way to quickly see before trying it. Of course, if you have a calculator, you can just divide by 3 and see if you get a decimal or not. But anyways. 4, you can determine that by looking at the last 2 digits in the number. If the last 2 digits are divisible by 4, then the whole thing is divisible by 4. 5, super easy, if it ends in 0 or 5. 10, kind of the same idea. If it ends in 0, 10 goes in. 6, the number is divisible by both 2 and 3. Notice that 2 and 3 are prime numbers, and 2 times 3 is 6. So if it's divisible by both of those, then 6 goes on. 7, there is a rule. Not the easiest to remember, but let's just divide by 7. See if 7 goes in evenly, then it's divisible by 7. 8, if the number's big enough, look at the last 3 digits. If those are divisible by 8, if that number formed by those last 3 digits is divisible by 8, then 8 goes into the whole thing. Not much use if the number is only 2 or 3 digits long, though. So just divide by 8 and see what happens. 9's pretty cool. If you add up the digits and they're divisible by 9, then 9 goes in evenly. That's going to be very useful in the near future when we're looking at some different codes, looking at some different check digits and things in like serial numbers and stuff. Also, there's something called casting out nines that you can use to check addition, subtraction, multiplication, and division problems. And it's based on this principle that if you add up the digits and that result's divisible by 9, then 9 goes into the whole number. And as I mentioned earlier, 10 just divisible by 0. Or ends in 0, I mean. Sorry. Let's look at a couple. Let's use the rules. Let's look at 23,800. And we want to decide if it's divisible by what it's divisible by. Well, if it's divisible by 2, the number must be even, which, just look at this ones place digit here. If that ones place digit's even, then the number is even. So yeah, 2 definitely works. We're not going to use 1. 1 goes into everything. 3, the sum of the digits is divisible by 3. Well, if you add up 2 plus 3 plus 8 plus 0 plus 0, you get 13. Well, 3 does not go into 13 evenly. You get 4 remainder 1. So 3 is not one of them. Number formed by the last 2 digits divisible by 4. Well, yeah, 0, 0 is divisible by 4. So this must be divisible by 4. And you can always put it in your calculator. 23,800 divided by 4 goes in evenly. Let's see, 4 times 5 is 20, 4 times 9 is 36, 4 times 5. So 5, 9, 5, 0. Yeah, it goes in evenly. 5 ends in 0 or 5. Well, this ends in 0, so 5 goes in evenly. 6 has to be divisible by both 2 and 3. Well, it's divisible by 2, but not 3, so 6 doesn't work. 7, let's try dividing by 7, see what happens. Ooh, it works. So 7 has it. Let's see, for 8, well, the last 3 digits just have to be divisible by 8. Yeah, that works. So that 8's 1. 9, well, over here we did the sum of the digits and got 13. 9 does not go into 13 evenly. 9 goes in with 1 remainder of 4, so 9's not an answer. But the number does end in 0, so 10. 10 works. So that's divisible by, so 23,800 is divisible by 2, 4, 5, 7, 8, and 10. Let's do one more of those. 170,820. All right, one's digit again is 0, so we know that it's even. So we know 2 is going to go in. We also know that 5 is going to go in, and we know that 10 is going to go in because of that 0 there. 3, the sum of the digits divisible by 3. Let's add up the digits. I already know 0 is not going to have a big impact there. So you add them up, you get 18. Well, 3 times 6 is 18, so 3 works. 4, last 2 digits divisible by 4. Well, last 2 digits is 20, and 4 times 5 is 20. So yeah, 4 works. We already looked at 5. 6 has to be divisible by both 2 and 3. It is. We already had 2 and 3. So 6 works. 7, remember you gotta just divide by 7, see what happens. Oh, this is not looking good. Could you bring down the 2? You have 20. 7 times 2 is 14. 6, bring down the 0. 7 times 8 is 56. Remainder 4. 7 doesn't work. 8, last 3 digits needs to be divisible by 8. I don't think 820. Yeah, 820. 8 does not go in evenly into that. Get a remainder of 4. So not 8. Going back to the sum of the digits, 18. 9 times 2 is 18, so 9 works. And we already decided 10 works. So now you have your pick, like when you're trying to do factors. You know that at least 2, 3, 4, 5, 6, 9, and 10 go in. So that helps you find some of your factors of that number. All right, so that's the divisibility rules. Let's look at one more major topic for now with prime numbers. Let's look at something called the fundamental theorem of arithmetic. Every composite number can be expressed as a unique product of prime numbers. All right, prime numbers already you just have like 1 times the number. But if you have a composite number, you can break it down into prime numbers that will multiply and equal the composite number. And every composite number has its own prime factorization. So that prime factorization can't belong to a different composite number at the same time. And every composite number definitely has one. Has this product of prime numbers. To find the prime factorization, one technique is a factor tree. I'm sure you've all seen these at some point. Common middle school topic. In the factor tree, you start with the number. Then you branch off with 2 factors of that number. Doesn't matter what 2 factors you use. I just would avoid using 1 times the number because that's not going to get you very fast the result. And then you keep taking each level or tier and you break down those factors into further factors. And you keep doing this until the very bottom tier is all prime numbers. And those prime numbers will be your prime factorization of the original number. For example, let's say you start with 198. Notice that first tier I broke it down to 2 times 99. 2's prime, so I really couldn't break that down anymore, so I just kept carrying it down. But 99's composite, so I broke that down to 9 times 11. Again, 11's prime, so that just got carried down, same as the 2. But 9 was composite, so I broke it down to 3 times 3. Now at the very bottom, I have all prime numbers. So 2 times 3 times 3 times 11. If you multiply those out, 2 times 3 is 6, 6 times 3 is 18, 18 times 11 is 198. You could also write that prime factorization as 2 times 3 squared times 11. That also equals 198. So that is the unique prime factorization for 198. That's the only prime factorization that 198 has, and 198 is the only number that has that prime factorization. Every composite number has one of these. Now when you're doing your factor tree, one of the first questions usually asked is, but what if I don't do 2 times 99 first? Well, that's okay. Do something else. Let's see, 198. 1 plus 9 is 10. 10 plus 8 is 18. Yeah, I can use 3, because 3 goes into 18. So I could say, instead of 2 times 99, I could say 3 times 66. That's perfectly fine. I would bring the 3 down because it's prime. And I might break 66 down to 6 times 11. You could use 2 times 33, 3 times 22. You know, there's other options. It's okay. It'll all work out in the end. 3 comes down, 11 comes down, 6 breaks down into 2 times 3. The prime factors are a little out of order there, but that's all right. Multiplication's commutative. Doesn't matter what order you multiply in. But just because I like to do this, I like to make sure, I like to put the numbers in numerical order. So 2 times 3 times 3 times 11. Same result as up here. The factor tree looked a little different going down. The second and third tiers look different, but the final result was the same. And that's going to be true. As long as you're choosing correct factors, it doesn't matter what factors you're choosing, Eventually, when you get to the bottom, you'll have the same prime factorization as somebody else that might have been doing the same number but with different factors. Just avoid using 1. That's not going to get you anywhere. I would not have started with 1 times 198. That would have just been a waste of time. I would have not done 1 times 66 or 1 times 6 anywhere in there because that would have wasted my time. Yes, so notice that 2 times 3 times 3 times 11 is 198. Also, your second tier could be different if you choose to start with different factors, and that's okay. All right, let's do another one. Let's do 98. My first thought when I see this is that it's even, so 2 goes in, and 2 goes in 49 times. 49, don't have much choice, breaks down to 7 times 7. So that's the same thing as 2 times 7 squared. You might see your prime factors written with exponents when you're done. But again, 98, somebody else might have been like, you know, that looks like something like 3 would go into. Let me look. 9 plus 8, 17. That doesn't work. What about maybe something else, like just for kicks and grins? Let's say they tried 7. 7 times 14. That works. Then I break 14 down to 7 times 2. And look at that. I got the same prime factorization. So it doesn't matter which pair of factors you start with as long as it's indeed a correct pair of factors. Eventually you'll get down to the same primes. Let's do 1336. My first thought is 2 just because it ends in 6 and is even. 2's prime. 668, I'm going to do 2 again. You might not choose to do 2 again. You might do something else, and that's all right. 2 times 167. 167, that one looks tricky. 167, well, 2 doesn't go in because it's odd. 3 doesn't go in because 1 plus 6 is 7. 7 plus 7 is 14. 4 does not go in. 5 does not go in evenly. 6 does not go in evenly. 7, 8, 9 doesn't. 10 doesn't. As soon as you hit 10, you're getting like 16 point something. 11 doesn't go in evenly. Neither does 12. And at that point, if you divide like 167 by 13, you get something like 12 point something. So now you're starting to get numbers less than what you're dividing by. So you run out. That must be prime. 167, you're not able to break it down any further. So the prime factorization is 2 cubed times 167. If you'd done a sieve of Eratosthenes up to 200, you would have ended up circling 167 as a prime number. Okay, let's do one more of those. Let's do 663. Oh, 3 definitely goes in. Not 2, it's odd, but 3 definitely goes in. 3 times 221. Let's see, 221 looks suspicious, but let's see here. 2 does not go in, 3 does not go in. 4, no. 5, no. 6, no. 7, no. 8, no. 9, no. 10, no. 11, no. Now I'm starting to get a little higher up. I'm going to do my calculator here. 221 divided by 12. No, that's like 18.416 repeating. 221 divided by 13. Oh, 13 and 17. There you go. Those are both prime. So actually we stopped there. 3 times 13 times 17. So we got all prime numbers. All right. So that's your prime factor trees. Keep learn those. Learn how to do those because you're going to need them soon. All right, some more historical notes. Kind of remarkable thing done in 1914. A machine was built in France by Carusson, two-factor numbers. But, I mean, it was used for a while, but it got stored away and left in a closet for a long time at this astronomical observatory. And then all of a sudden in the 1990s, Geoffrey Challet from the University of Waterloo found it, hiding in this closet in France at this astronomical observatory. And it turns out this machine's pretty remarkable in that it can process 35 to 40 numbers per second. When you consider that our first known computers were actually invented during World War II, that's a little side trip later too, where during World War II, you had super secret operations both here in the US and in England. And in England, it was at a mansion called Bletchley Park. And you had gentlemen named Tommy Flowers and Alan Turing, which will come up later again, but they were responsible for inventing the world's first computing machine that we thought. That was the beginnings of our modern day computers, very beginnings of what my iPad I'm using right now to record this. But so that was 1930s and 40s. They're working on that. They had no idea that this other machine had already been built that could process that many numbers and do factorizations. And we didn't know it until the 1990s when somebody figured it out, like found out and found it in this closet. Pretty cool, huh? Another person that's kind of, I think is interesting because the whole factorization thing, Mr. Ramanujan, he wasn't wealthy or anything when he was born. He was born in India, an impoverished middle-class family. But he taught himself higher math, which is pretty amazing. He was a brilliant genius. He ended up studying with G.H. Hardy in England. And one of the kind of cool stories that Hardy would tell was that he and Ramanujan were riding a cab together when they first knew each other. And Ramanujan noted that the license plate number was 1729, and immediately it was able to say, that's the smallest positive integer that can be represented in two different ways as the sum of two cubes. It was like, he looked at it and like, that, figured this out. And it's like 1 cubed plus 12 cubed, or 9 cubed plus 10 cubed. Yeah, put it in your calculator and check it out. It does work. Both of those come out to 1,729. Okay. So add him to your mathematician list, and then be sure to join us again very soon for a continuation on the discussion about prime numbers. Thank you for joining me.